Now that we have a little bit of background knowledge on natural log and what it was, so now we're going to look at how do we derive it. So we're going to look at what if it's just the natural log of x, and then what if we're trying to derive the natural log of some function of x, which we're going to use the letter u to indicate that inner function again. So the derivative of natural log of x is actually pretty simple. It is just 1 over x. I do mention here that you can't have x be 0, can't plug in a 0 value for that because it would be undefined. For the overall, more of the general way that we derive it, the derivative of the natural log of u is the derivative of u over u. So it's the derivative of what you're taking the natural log of divided by that original piece you're taking the natural log of. And that's what a lot of them will be. Instead of the natural log of x, it'll be the natural log of x squared plus 5 or something like that. A more complex function is kind of that inner u layer. So I have some really basic examples here, kind of take you through some different options that you could see as you're practicing these. We do tend to stick a lot with natural logs that are relatively simple. So my first one, I have the natural log of 4x, so it's going to be the derivative of 4x over 4x. So the derivative of 4x is 4 over 4x. You can do basic simplifying. You can cancel the 4's to get 1 over x. Next one, natural log of x squared plus 4. So you're going to take the derivative of x squared plus 4 over x squared plus 4. And this actually will not simplify at all. Number 3 is kind of a trick question. E is a number. So the natural log of e is just 1. And the derivative of 1 is 0. So anytime you have something that doesn't have a variable, remember e is not a variable, it's actually a number, your derivative will be 0 because it is a constant. These two show you why it was important to review all those properties. So when you're taking the derivative of a natural log, if it's kind of a complicated piece, it is possible that you might be able to use log properties to make your life easier. So here's what I mean by that. In this current form, the natural log of the square root of x plus 5, it would kind of be messy to take that derivative because you'd have a kind of a chain rule working in there. We can actually rewrite that because it's currently to the 1/2 power, bring that power in front. So you can expand using that logarithm property that says the power is allowed to come out front. Now, when you take the derivative, you can just keep that 1/2 out front and do the du over u. So the derivative of x plus 5 is 1 over x plus 5. So you'll find that those logarithm properties, they didn't seem very useful in Algebra 2, but they're actually very useful in calculus to, again, make our life easier. And that's really what algebra does for calculus. So if you look at this next one, this is one that you really are happy to have properties, because if you had to derive x cubed times the quantity x squared minus 4x all to the 5th power, it would be a total mess. It would be a product rule and chain rule. But with properties, I can split that all up. So I can say that that's 3 natural log of x plus 5 natural log of x squared minus 4x. So pulling powers out front, pulling apart the multiplication. Then I can derive term by term. So the derivative of 3 natural log of x is just going to be 3 times 1 over x, or you can write it as 3 over x. The derivative of 5 natural log of x squared minus 4x is going to be 5, and then du over u, so the derivative is 2x minus 4 over the original x squared minus 4x. So by expanding, so the idea is if we expand first, it makes the derivative so much simpler because you aren't using a lot of complicated rules to derive. You're really just sticking with the main rule, which is the derivative over the original. You can have additional rules show up with natural log, though. All of those rules that we learned back in chapter 2 are still fair game. So I did one here that's a product rule and one here that's a quotient rule, so you get a little practice with that. So with our product rule, first times the derivative of the second, so the derivative of the natural log of x is 1 over x, plus the second times the derivative of the first. Derivative of x is just 1. You can actually clean this up a lot. You end up with just 1 plus the natural log of x as your answer. For the next one, we can do a quotient rule. So bottom times the derivative of the top. The derivative of the natural log of x is 1 over x, minus the top times the derivative of the bottom. I'm going to do the derivative of the bottom first. Kind of like trig. I don't like to put something after a natural log that's not part of it. All over the bottom squared. And again, minimal cleanup. You could cancel 1x here with 1x here and write it as x minus 2x natural log of x over x squared. You could even go a step further if you want and cancel 1x from every term. Not necessary, but something that you might see on a multiple choice. So, finishing with some special situations here. If you're working with a natural log that has an absolute value around what you're taking the natural log of, it doesn't change the process. So, I wanted to mention that because when you see natural log of trig functions, you will see an absolute value around the trig function, whatever it is, sine, cosine, tangent. And the reason is trig functions tend to bounce back and forth between positive and negative, and this is just ensuring that we're only working with a natural log of something positive. So again, does not change the rule, but I just wanted you to see that. So if you see absolute value, you don't get scared that you're missing something you're supposed to be doing. So it's still, this is my u piece, it's still the derivative of that over that. So the derivative of cosine is negative sine over the original cosine. And you can leave your answer like that, or you may notice that that is one of our basic identities, that is tangent. So you can write your answer as negative tangent. Next one, derivative of 1 plus sine t is cosine t. Looks like the word cost. And then over the original. And that does not simplify. I know it kind of looks like there should be some sort of identity, but there is not. And then the last one, secant, the derivative of secant is secant tangent over the original u, which was secant. This one also will do some really quick simplifying. You can cancel your secants and get just tangent. Last special situation is what happens when you have a natural log inside another natural log. I often call them an embedded natural log. These are not super common, but sometimes you'll see a really basic one, and I want to make sure you know what to do with it. So you kind of work inside out. So like that, you go start with the innermost piece. So to take the derivative of the natural log of x, you would get 1 over x. But then that whole thing is over the natural log of x. So this is your u piece. You're taking the natural log of the natural log of x. Your inner u piece is the natural log of x. So you're going to take the derivative over the original. The derivative of natural log of x is 1 over x over the original. Now you're welcome to leave your answer like this, but a faster way to write your answer would be to put both terms in one denominator to kind of combine denominators. Same thing with this next one. You're going to take the derivative of 3x plus 2 over 3x plus 2 over the natural log of 3x plus 2. And again, you can leave your answer like that, but you'll often see it written as one fraction where the two denominators are just multiplied together. But that's some of the different ways that you'll see natural logs show up with derivatives. You're going to have natural logs with trig. You're going to have natural logs with product rules and quotient rules and properties. You're also going to have some on Delta Math that ask you to find slope or to find the derivative at a point. So with those, you'll have to plug an x value in. You'll notice with all of these, though, you are just plugging in an x value, and then that will give you your slope or the derivative at that particular point.